is to create something that will.
Well, hello everyone. Having some technical difficulties, knew there would be for round number 1 of the live stream. So, hello, my name is Maiden, and today is September 1st, 2019. I'm your host of this crazy, wild podcast that's probably, it's a work in progress. So it's just going to be myself today. I'll have guests on later on, but the purpose of this podcast is kind of open up conversation and dialogue through a whole bunch of different mediums, and how we can first talk about things that we can do to change and talk about things that are going on in the world, and then actually put them into action, what we can do. But first and foremost is just to open up a conversation about whatever craziness is going on in the world. And to start, like I said, my name is Maiden, and I'll just go over my story, a little bit about myself. This maiden voyage is what this stream will primarily be about. So the number one question I get asked, first and foremost, is Maiden. Like, how'd you get that name, Maiden? So when I was in my mom's womb, my parents said, when you hear a good name, kick. And so they named a bunch of names off from a name dictionary, and I never kicked. They even joked around with some names like Jack and Harry, so Jack Axe, Harry Axe. Wouldn't go over very well, I don't think, in school. And they went through a plethora of names for about 4 or 5 days until my oldest brother, Steve, he was reading this science fiction book by an author named Hebrew Jens, who's a ex-Scientologist, or he was part of Scientology. I'll get into that story later. But he was reading this book, and he came running from downstairs during breakfast, I believe. He's like, "Hey, I have a perfect name, Maiden." And right then I kicked. And the name, or the character in the book, was the intergalactic Moses. He freed the slaves, freed the slaves of the cosmos. And it's supposed to be, its origin is Greek, but it's not part of the pantheon. But it means general of the gods is what the author created it to mean, I guess. But it's not from the real Greek pantheon of gods or anything like that. And it also means free from envy in Gaelic. So that's how I got my name. And so my story begins in Bellevue, Washington. That's where I'm from, in the U.S., obviously. And so I was born from some very interesting parents. My mom all 3 of my parents were in Scientology, and that's how they met. My mom is a very spiritual person, and she is a therapist. She's a trauma therapist, and she's always been very connected spiritually, and she truly is an angel. I mean, I'm so blessed to have the mom I have. She's always supportive of me, always there for me. My dad, however, my real dad, he wasn't around too much, and he was off doing his own thing. He's kind of the polar opposite of my mom in a sense. When he was around, he was very supportive of me and would ask me lots of questions to get my mind going. And he's very intellectual, but he was also very self-consumed, and he did some crazy stuff. One being, when he was in Scientology, he went over to the Philippines when Marco was in rule. I don't know if you know Marco. He was a dictator of the Philippines. The story goes he got in close with him with book sales and stuff, because Scientology, if you don't know anything about Scientology, it's basically kind of a spiritual cult in a way that sold books. L. Ron Hubbard sold books and stuff like that. And if any Scientologists are watching this, I apologize. I mean no disrespect to your belief structure. It's just my parents saw some shady stuff that they would do, so they got out. But he was selling books in the Philippines and got in good with Marco, one of Marco's men, and stumbled upon some gold bars. And at the time, Marco's crap was kind of going down, where it's getting a lot of pressure, and the U.S. was intervening, and my dad saw an opportunity, I guess, to take some gold bars, and that's what he did. And then, Marcos's men were on him for a while, but because Marcos was going down, he got away with it, I guess. So that was just one story, but he's got quite a colorful past of shady deals and stuff like that. Very self-absorbed type of person, unfortunately, although I love him very much. And then when I was about 10, my parents got a divorce and they separated because of my dad being the way he is, my mom being abused essentially. I grew up with another father figure in my life, and he's actually one of the very first father figures I ever had, but I didn't really recognize it that way until later on. But my father, Michael, my stepdad, he's like my real dad pretty much, because he's been there for me. He's actually been there for me whenever I needed anything. So, and he was also in Scientology with my parents, and so they'd known each other way before I was ever born. And when my parents got divorced, he, I guess always had a thing for my mom. You know how it goes, and they started hooking up, meeting up, and I moved in with my grandpa, and who actually just passed away recently. And my grandpa was kind of like the first real father figure in my life, because he was always there and would help me with engineering. So he was an engineer, Army engineer, and he'd help me with engineering stuff or math, and which I was terrible at. I wanted nothing to do with, but he would help me out. And then my stepdad came into my life, and long story short, I was raised by these other fatherly figures that very much get things done, and I'm so blessed. I'm so blessed not only to be alive, but also to have the father figures that I have. I don't know where I'd be if I didn't have the father figures that I have in my life. So appreciate that. That's my story. So what am I all about? So for the longest time, it's been going on 5 years now. No, actually 3 years solid. So I did about a year of research first. I've been working on starting my own businesses. I started one main of my own business, which is C Digital, as you see here. And I'll bring up a Google search bar so we have something to look at. And I started my own business. Been doing my business for a while now, and it's essentially just digital marketing stuff. And then I have an e-commerce store that plays into my passions and the things I love, which is creating engineering things, and trying to honestly make the world a better place, both by not so much by my words alone, but my actions. So for about 7 or 8 years now, though, I've been working on oops.
Hit my eye.
It did not.
Yes, it did.
Are you okay?
What was it?
Please,
I've been-
don't throw a pen at me.
I didn't mean to. So for 7, I threw something at him, but I didn't know it was a pen. Yeah, if he could be a little quieter, but. So anyways, where was I? So just not only with my words, but with also my actions, right? And so for 7 years, that's where I was at. For 7 or 8 years now, I've been working on a fusion experiment that has some interesting properties to it. So one of them being that it boils water extremely fast, and it's not something that I came up with originally. Like, I've just adapted to older things in the past, like Martin Fleischmann and Stanley Pons, and obviously Nikola Tesla, and some other people in between. Some Russian gentlemen that I'm unable to say their names, besides Parkmanov, but no, there's many others in the past. Just people in the past, and really that's kind of where Conscious Energies comes from. Like, that's the idea behind it, is that the people of the past have built us and brought us to where we are. Like, people, every day I wake up, I'm so grateful from just like the people of the past, besides just my parents and stuff like that. But there's so many people in the past who have helped us, get to where we are and build the structures that we have in place, whether you consider them to be good or bad or whatever. So I was looking for some flashy background stuff. I'm just going off the cuff on this one because, like I said, this is the first round of me talking, and the future episodes will have guests and stuff like that. But if you guys ever have any comments or anything, just let me know. I don't expect there to be too many people watching this. I haven't made any videos on this actual YouTube channel in quite a long time, so it's probably died off a little bit on the algorithm. But what we can do is go into, and I'll talk more about my experiments and stuff because I'm still actively working on it. Science news. I'm still actively working on that stuff. Actually, I just got a garage to be able to do it some more, so a laboratory, and that's where I'm at with it. I'm actually going to be moving a lot of this stuff out. If I turn the camera right here, you can probably see it. Besides this, you can see all that stuff over there is my tiny lab. But like I said, I have a garage space now, so I actually have a laboratory, which is gonna be awesome. But I've got a lot of stuff to move out and sell first. So shedding light on black holes. Let's get into this. Let's have a reaction to this crazy stuff. I have my own personal opinion on black holes.
On black holes.
It's different than the mainstream, but that's okay.
Presented by science at NASA.
That doesn't matter. NASA.
Black holes
very respectful.
is one of the most highly searched terms about our universe.
Ooh.
There's a fascination with the idea of a region of space having a gravitational pull so strong, nothing can escape its deadly grasp.
So there's the first kind of issue I have with black holes is that we haven't been able to sense gravity yet as a particle. It's just force, right? And it's a force derived from mass, is what they say. However, in physics, or in applied physics and in research for quantum physics especially, we still have yet to find any evidence of a graviton or gravity in general. All we can find is the force that applies on things. So it brings into the question, does gravity even exist? And how would we substitute gravity, or what would be a substitution for gravity, since we obviously can see, and nature shows us, that there is a force being applied on all things with mass. But the question is it gravity? That's because of our own old Newtonian ways of thinking about things. We haven't been able to separate from that and maybe reformat it from its foundation. Instead, we just build on top of it. And so let's continue.
Not even a sliver of light. Well, not quite. In fact, much of what we think we know about black holes turns out to be myths. Myth 1. All black holes are black. As this photograph from the Event Horizon Telescope demonstrated, light can be detected near a black hole's event horizon. This is the boundary between normal space and the space affected by the black hole's gravity, from which
So, in this picture too, it's a really popular picture now, and all of our sensors and everything, the way that we've figured out how to find black holes in the universe is through theoretical calculations. So, we have the LIGO. We have the LIGO sensors, which are basically interferometers that have lasers between two mirrors, and this is just a quick explanation, and if those two mirrors vibrate in any way or change in any way, that laser will sense it, and it's extremely, extremely sensitive, and these mirrors are suspended 4 times, and they're in a vacuum chamber and all this kind of stuff, right? and it's over a very long distance because the wavelength of gravity is so big, I guess, that you need a long space in order to be able to see it. And so we saw movement in it that was supposedly within the range of margin of error, as well, or beyond the margin of error, I should say, as well as had, what we would consider the tall tale signs of black hole. But that's kind of where you get into this. There's a difference between inductive reasoning and deductive reasoning. And inductive means that you've already have an idea of how something's going to be, so you're inducing your opinion into it. I think that's kind of where it gets its terminal, or its origin from, its root, and you're introducing your ideas, right, to test to see if the experiment is to your theory. And then deductive reasoning is where you have something that's happening in nature, right, and you deduce, you break down all of its components to try to find why nature is doing that and build your theory upon that. So it's just like a top-down or bottom-up type of way to do science, right? So I noticed that with a lot of mainstream science, it's a lot of inductive reasoning, and there's a theory that we don't want to let go of, right? We don't want to change about gravity, and some of Einstein's, of special relativity and some of these ideas about gravity that we don't want to really change. And because of that, we're doing experiments to, instead of break it down, actually build it up. So it doesn't fall. It's like this hybrid of the two different ways to do science, and it's not necessarily a great way to do science. I will say, like, the LIGO interferometer is really cool because there's obviously phenomenon happening, and there's energies or forces being applied on the Earth that we can measure, but we still haven't been able to detect gravity. So how could we say it's a gravitational wave? Like, it might be something else. There might be another avenue. So something to think about.
Escape is possible. Part of this light comes from the black hole's accretion disk, a flat pancake-like structure composed of dust, gas, and other debris. Friction constantly moves the disk's material inward toward the event horizon. Light also comes from jet streams, which propel matter outward along the disk's north and south poles.
So I'm not going to inject too much of my beliefs on this, but it's something to think about. If you know anything about electrical engineering or just electricity in general, it's something to think about even how friction and heat are made. It's electrical in nature. It's just something that's not talked about very much for some reason. We just want to automatically assume, because it simplifies things, that when two things rub up against each other, that they get warm, right? And so that's friction, and then that's it. But if you go in deeper to what creates friction, it's actually an electrical phenomenon. It's something to consider and think about. It has to do with phonon vibration. Phonon is different than photon. A phonon is actually moving the molecules of the structure, and because they're bouncing around and moving so much, they create Coulomb friction, or their electrons are getting excited because there's energy in them. So because of that, they're creating heat. That's where the friction happens, is the fact that these atoms are bumping against each other and rubbing against each other. Like, and the more you bump them and rub them, the closer they get. The more that they are going to fuse together, but it takes extreme heat and all that kind of stuff, supposedly. That goes into my research stuff, but anyways, let's continue.
Myth 2. All black holes are about the same size. Black holes actually come in several different sizes, which are defined by their mass. Small black holes are usually the result of a relatively short and violent collapse of a star. Recent work suggests that intermediate black holes are found in the nuclei of some active galaxies. Supermassive black holes, on the other hand, are found at the center of nearly every galaxy. Dr. Dan Evans, an astrophysicist at NASA headquarters, says there's a direct relationship between the beginning of supermassive black holes and the beginning of their corresponding galaxy. This strongly suggests the two were born about the same time and slowly grew in size together over billions of years. Myth 3. If
Interesting.
you get within a few thousand miles of a black hole, its supergravity will
Pull you into the
its
center.
It turns out you can get surprisingly close to a black hole. If you approached a black hole with a mass equal to our sun's, for example, you could get as close as tens of miles. So imagine if we replaced our sun with a black hole of the same mass. All of the planets would continue to revolve around it at exactly the same speed and distance as they do now.
So, interesting to think about. So, if you have a black hole that's supposedly sucking all the material in from the universe around, but yet it doesn't unless it's passing by 10 miles, think about the probability of what they just said. So it makes you question, like, okay, well, if that's the case, right, and if a black hole's passing through a galaxy, but it has to be within, 10 or let's give it 100 miles even, right? That's 1,000 miles. That's nothing. That's nothing in the universe. Like, that's so the probability of black holes being able to scrape up dust and debris throughout the universe, like it would take a very long time. But then you think about trajectory and how it would be moving through space and spinning at the same time, and it makes you like wonder, well, wouldn't you see like a three-dimensional helix rather than just a spiral accretion type of disk, and then it makes you wonder, like, okay, well, that's a little strange. Like, how come that's a myth, right? How come we all talk about black holes sucking all the cosmic debris in,
Myth
right?
4. Once inside a black hole, nothing ever comes out. Nope. It turns out that radiation can escape from a black hole. One of Stephen Hawking's contributions was a theory that a black hole is not so dense in a quantum mechanical
Keyword theory.
sense. The slow leak of what's now known as Hawking radiation would, over time, cause the black hole to simply evaporate. The image from the Event Horizon Telescope confirmed what Albert Einstein's general theory of relativity predicted.
See, and once again, a lot of scientists are trying to confirm old theories, and so it makes it. Sure. Sorry, interruption. So it makes it very difficult to, if you're opposed to that theory, it makes it very difficult to present your data and show your opposition. Immediately you can become ostracized. Well, this has been built up for so long and all that kind of stuff. But really the whole key to science is to disprove what's currently in place. So, and again, this is where I guess I go kind of deep in a lot of senses. The fundamental reason behind why many sciences don't really advance. Thank you. Coffee. Don't really advance is because of our social structure, underlying way that we operate as human beings is with a monetary system, right? That kind of supports scarcity and the idea that there's finite of everything and makes it very competitive. And because of that, we have educational systems that need funding, right? Well, if you present data that's going to ruin all of these other projects around it that have been going on for years, tens of years, then it'll ruin all their it'll destroy all their funding. So they're very much opposed to a lot of that setup, right? And having to retool everything. It's kind of like right now with AI. Like if AI was just to be introduced tomorrow that actually worked, it could actually, like an AI system that could manufacture itself, build manufacturing facilities and expand and be able to eliminate all of our jobs. Let's say this is totally theoretical, and if that was to happen like tomorrow or in a couple, it would be over a couple years of time. But let's say it just started tomorrow. Somebody came up with the way for self-recognizing AI. The disruptive power of that, right, to eliminate all the jobs, like that would be, people would be very opposed to that unless it was introduced radically, right? And it's the same kind of principle. Like people are very opposed. It'll break all the structures, So that's usually why and it's a healthy thing too if you think about it. I'm by no means complaining or saying that people are wrong, but it's a healthy thing because it keeps things checked and balanced in a way. Like, you have this new radical idea of science. Well, people who already have an upheld belief of this particular scientific discovery will try to poke holes in it as much as possible, and that's how science should be done. That's really, really healthy, and it prevents things from just being released radically and disrupting current systems in place that could hurt us potentially. But then at the same time, there's a balance to that too, right? It's always about balance. So let's keep going.
Over 100 years ago, that a black hole's form is that of a perfect circle. And as scientists learn even more about the properties of this gigantic cosmic mystery we call a black hole, they'll be able to puncture even more myths. To hear more true tales
So
about
pretty
black
interesting
holes,
stuff, right? Now, let's go to our friend YouTube. If any of you guys have any questions or anything like that, you let me know. And yeah, I mean, I gotta find good audio too, because this is gonna be streaming on a podcast as well. So I gotta make sure that I have some good audio. And let's look into. We're gonna look into low temperature superconductors. And we'll try to find a good one here. Seeker usually has some good stuff as far as explanations. But there's a breakthrough. Let's look into this breakthrough. Sounds fun. At room temperature.
Grammarly does
And we're
more
gonna get a
than
commercial.
catch errors.
So bear
With
with me
Grammarly,
here.
you can
There we go.
It's been over a week since the Indian Institute of Science breakthrough on superconductivity has again created news. This time, the research supervisor-student duo of the Solid State and Structural Chemistry Department came out with a clarification on the paper they posted on ARXiv the last year, claiming that they found superconductivity in ambient temperature and pressure. Why is this important? Let's have a rundown. So the authors of the paper, Anshu Pandey and Dev Kumar Thappa, both the research scholars of IISc, claimed that they had discovered superconducting behavior at room temperature and
Silver
pressure
and gold
in a
composite
nanostructured
materials.
composite material of silver and gold formed by embedding silver nanoparticles in gold matrix. So what is a superconductor? Superconductors are materials that exhibit perfect conductivity of electricity and perfect diamagnetism. So perfect conductivity here means zero resistance to electricity and thereby zero.
So, but think about this: if we made for one, silver and gold, extremely precious metals, right? So first thing to think about. It'd be great for electronic components, but world scale, like, I don't know how that's gonna work. Two is we're talking about organizing nanocrystalline lattices, and that's takes a lot of money, right? To put it in a general idea, or to look at another way, it takes a lot of equipment and technical skills. So it equals a lot of money and a lot of time, and probably a lot of energy too to create it. And so that makes it very expensive. So, an engineering standpoint, this is the beginning of something, perhaps, as if these claims are true. But something to consider. It's pretty expensive.
Power laws. Whereas perfect diamagnetism implies strong repulsion when a magnetic field is applied. Superconductivity, since its discovery by the Dutch scientist Kamerlingh Onnes in 1911, has always been a holy grail in the material science. It gives the possibility of generating, transmitting and utilizing electrical energy without any loss. So the fact that such materials exhibit strong diamagnetism means that we would generate very strong forces that can work against gravity. For instance, you can have a bearing that is both frictionless and contactless. These strong forces can even be utilized for fast ground transportation of trains. In fact, superconducting trains can travel with high speeds without any contact with the ground. That is, the trains can be levitated above the ground. You might think that life would be so easy with superconductors. No. the prospect of superconductors also come with a lot of conditions. Materials
Exactly.
that exhibit this property have only done so when cooled to sufficiently low temperature, close to absolute zero, that is 0 Kelvin. Achieving this level of temperature is highly expensive.
So here's something to consider now. How cold is space, right? This is why it ties into kind of a black hole, and like a lot of my research I've done for quite a while now. But how cold is space? How cold does space get? We'll go into some other interesting condensed matter physics and condensed materials, basically.
And at the same time, an energy consuming process. That is why material science experts have always tried various combinations of metal and other elements to achieve superconductivity at high temperatures. Given that the claim by IISc research scholars last year then took the entire science community by surprise. Many initially dismissed the claim, pointing out insufficiency in details and indicating flaws in the data. However, this time, they have revised their claim with more measurements and an elaborate team standing by the claim they made earlier. So if they are able to categorically prove their claim of observing superconductivity at ambient temperature and pressure in a nanostructured gold-silver composite material, this will revolutionize electrical transmission and high-speed transportation worldwide. And India can hold its head high for that.
Not if it's made out of gold and silver, though. Right? That's gold and silver nanoparticle lattices. It's expensive. It's going to be expensive. So
even a physics Nobel for the taking. We love science, and if you do too, like, share, and subscribe. Your support will.
So there we go. So now let's look into something that's a very interesting phenomenon in space, which is fluid dynamics, which we know exists, and it's how we model a lot of things. Only gravity is the factor for our model. That's what we label its formula, right? Its formula in these computer models. But check this out. It's a really interesting phenomenon that nature is showing us. It's called superfluidity. So superfluid helium. Well, I like some of the classic videos of this. Let's see if I can find them here. Liquid helium. I can't seem to find like the original. It'd be rad if I had like that guy pulling up something in the back. Oh, advertisement. I gotta.
Thanks to Brilliant for supporting this episode of SciShow.
We'll go to SciShow for some info.
Brilliant.org/SciShow to learn more. That it was still spinning. Now imagine you picked up for 5 minutes and came back to see that it was
start over.
Imagine you made yourself a cup of tea, stirred it, left it for 5 minutes, and came back to see that it was still spinning. Now imagine you picked up that cup and the tea fell straight through the bottom while also starting to climb up the sides of the cup to flow out the top. That might sound impossible, but if your cup was full of helium cooled to about negative 270 degrees Celsius, that is exactly what you would see. Because at that temperature, helium becomes a weird substance known as a superfluid. It's part of a world of ultra-cold phenomena that have won theoretical and experimental physicists alike several Nobel Prizes.
So a fluid that defies gravity. Interesting, right? Super conductive fluid as well. Very, very interesting.
And it might even hold the key to understanding the nature of space-time itself. To understand how superfluids work, it helps to know a little bit about how particles behave.
Space-time, so what is one of the fundamental parts of Einstein's equations that talk about gravity and how gravity warps space-time? Right, so very interesting part of physics where nature is telling us. So goes back to when I was talking about inductive to deductive reasoning. You know, this is more like nature's telling us something, and now we need to understand it. Just like nature tells us that gravity exists, right? The phenomenon, the force that gravity applies, that things are, that gravity's affecting us. But rather than just making theories and building up past theories that people have had, recognize that the experiments that those people that did, like Newton, for example, the experiments that he did in the past were spot on, and it didn't scale, and so that's when Einstein came in and tried to help scale it. But he built upon a theory of an energy that we can't find. We can't find the gravity energy. All we can see is the force of gravity. So yeah.
Thanks to quantum mechanics, things like atoms and molecules can't have just any old amount of energy. Instead, their energy comes in discrete levels. In other words, an atom or molecule can jump between different energy levels, but they can never be in between those levels. This is true for any molecule, but in everyday life, you don't notice this. There are just so many randomly moving particles out there.
This brings us into heat, like we talked about, and the fact that they're jumping energy states, right? Like I was saying. And so heat is, and friction, as it's called, is a part of the electrical phenomenon. I mean, it really is.
That other effects outweigh the quantum ones. But when you cool things down, the situation starts to get a little bit strange, especially when it comes to helium. At low temperatures, most things just freeze and become boring blocks of ice. But helium is unique among the elements in that it basically never freezes. At atmospheric pressure, it remains a liquid pretty much all the way down to absolute zero, which is negative 273.15 degrees Celsius, also called 0 Kelvin. But things get even weirder before you hit that point. When you get to the negative 270 degrees range,
So absolute zero is not absolute. We're constantly breaking records of how cold we can get things. It's a moving target, just to clarify.
just above 2 Kelvin, it's like liquid helium totally forgets how matter is supposed to work. This happens because the atoms are falling into lower and lower energy states as they cool down, and as liquid helium gets cold, more of the atoms fall into the same low energy state. This is when the weirdness really starts, because the rules of quantum mechanics mean that when the atoms are on the same energy level, they start to behave in unison. They literally become mathematically indistinguishable and all behave the same way.
So they become organized and they all move together and are structured in a lattice, right? Basically a fluid crystalline lattice, which is really interesting to think about.
So they don't bump into each other or even move in different directions like a regular liquid. Instead, all that is replaced with the perfectly coordinated unison of a superfluid. Because they're all moving together, there are no atoms bumping into and sliding off of one another, which means that there is zero friction between them. Start stirring and they will basically never stop spinning. The liquid can also slip past anything. Itself, the walls of a container, even microscopic cracks in the bottom of the beaker it's in. And if you don't have a perfectly tight lid on your container, the helium will straight up go rogue. All liquids tend to climb the walls of the container they're in, but usually the friction between the walls and the liquid are enough to counter that effect. That is not true with superfluids. They will get pushed right up the walls and over the top of the container. This can happen even with the septillion atoms in a beaker on a lab bench, which is inconvenient but also amazing because it's a purely quantum phenomenon that you can see with your eyes. Now, to be totally clear,
There's another quantum phenomenon you can see with your eyes, and it's high voltage electricity, light. There's another one. But just to put it in context, nature is showing us something, right? That's seems pretty important.
these effects don't work with just any helium atom. It specifically needs to be helium-4. Helium-4 has 2 protons, 2 electrons, and 2 neutrons, and that configuration means that the atom behaves like a type of particle called a boson, which is known for its ability to occupy the same energy level as its neighbors. Only these kinds of atoms can...
It's an easier way to put it, besides putting a fancy scientific the scientific discoverer's name on it. Actually, boson doesn't even have anything to do with necessarily. I shouldn't say anything to do, but boson is he studied completely different things. Anyways, a thing to look at it is like the difference between symmetry and asymmetry. So things being all lined up nicely, right? Like, you have a cube, or you look at it like plutonic solids, if you know anything about that. But basically geometry, just the geometry of it lining up nice and neat. or being crazy and chaotically dispersed. Like that's the difference between symmetry and asymmetry. So it's a very symmetrical particle, or symmetrical atom, I should say.
And slip into that low energy state together and become a superfluid. Helium-3, which only has one neutron, can't do that because on a quantum level, that missing neutron means it behaves differently. Well, for the most part, it turns out that helium-3 atoms can sort of team up in pairs called Cooper pairs, and those can behave like a boson.
So a Cooper pair is the same thing that happens in a superconductor too. Also something to consider. So a superconductor, well, hopefully he'll go into Cooper pairing, but like the low temperature superconductors, like we just looked, the video we just saw, also plays into this.
Meaning that they can condense just like atoms of helium-4. This means that you can make a superfluid out of them, but helium-3 and helium-4 superfluids behave differently. To get helium-3 to work, you have to cool it down to less than 3 millikelvin. Yeah, that's 3,000ths of a degree above absolute zero. By contrast, helium-4 only needs to go down to 2.1 Kelvin, which sure is warmer, although, you know, still very cold, colder than the most deep of deep space. And also to make things more complicated, helium-3 is only about 0.0001% of all of the helium found in nature. Most of the stuff around today comes from nuclear reactors. So making any superfluid is hard, but making one from helium-3, that is worthy of a Nobel Prize or two. Even though they are weird and amazing,
So rare.
superfluids are more than just an interesting quantum quirk. Research suggests that superfluids might make up the cores of neutron
Oh.
stars, which are tiny, dense objects in space made almost entirely of neutrons.
Interesting.
Superfluidity is also closely related to other weird quantum effects like superconductivity, where electricity can flow through wires with zero resistance. If we could control superconductors better, we could make batteries that never degrade, better quantum computers, lots of other useful things. There's even an idea out there that space-time itself might be a superfluid,
Oh, look at that. Look at what they're saying.
which may help in the long quest for a theory of everything. This is the theory that would explain both very large and very small systems, and scientists have been searching for it for years. This just goes to show that sometimes in physics, messing around with some equations on a chalkboard or just some chemicals in a lab bench can lead to discoveries that can change the world. All of these discoveries started with one big idea and one basic step, whether it was learning more about physics or getting better at problem solving. And if you're looking for a next step of your own, you might like brilliant
Then the advert. So, pretty interesting stuff. Helium. Helium is relatively abundant in the universe. We can take a quick look and I will tell you for sure. Helium amount in the universe. Helium amount in the universe. So that's why by mass, we say 75, 76% was hydrogen and 24% helium. Let's see how much helium is in the universe. Maybe we'll go that. Helium. How much helium is in the universe? Theoretically, right? Here we go. I can't quickly find it. We'll go to good old Wikipedia. It might be the second most abundant element in the universe. Actually, that might be a better way to look at it. Most abundant elements in the universe. We'll look in the wiki itself and see if they can give us an answer. Mounds of elements. Mounds of chemical elements. So, yep. The most common elements in the Milky Way. So that's our model. So this is using spectroscopy. Okay, bye. Thank you for coffee again. Is hydrogen followed by helium. So that's so that's answer that question. Now to go on to something very interesting is hydrogen super fluid. Is there hydrogen superfluid? So on YouTube, super solid. So this is not to say super solid, but what is it? And what does it do? It pours itself. Liquid that pours itself. Okay, so then there's what's called metallic hydrogen. Metallic hydrogen, quantum vortices, that looks cool. What I'm looking for though is, can superfluid link to understanding dark matter? Also another really good way to look at things. So now I'm not seeing anything on superfluid hydrogen. Now there is something called metallic hydrogen, but that's hydrogen usually trapped in a metallic structure, but we'll see what Seeker has to say after this short commercial break from Samsung. Okay, that was really
Solid, liquid, gas,
Super solid, super fluid.
or Bose-Einstein condensate.
That one is super cool.
It is plus plasma.
But we haven't even gotten started yet. We truly live in the future.
You ready, T?
Ready.
Scientists have created yet another state of matter.
Yay! It's called a super solid, and while it sounds like a solid, it's...
It's not.
Not.
A super solid is basically a super fluid that got its crap together.
And by
just like helium. So interesting, right?
crap, you mean molecules.
I do. The researchers who created the new state of matter took a Bose-Einstein condensate made of sodium gas and used lasers to cool it to near absolute zero.
The atoms are moving extremely slowly. A BEC is a special phase of matter created in 2001, winning researchers the Nobel Prize for Physics.
Once cooled to a BEC, the sodium flowed with zero friction. It's like a super fluid, which is awesome. The BEC was also superconductive, meaning its electrons move through it with zero resistance. There are numerous scientific benefits to these two conditions, but we're not here to talk about that.
In this case, the scientists kept cooling that sodium, and at some point it arranged into a non-crystalline solid.
The scientists called it a superfluid flow with long-range spatial periodicity of a solid.
Super simple.
Fancy science.
Yeah.
They sure are. Essentially, think of it like a coffee cup filled with a frictionless superconducting gel that if you could stir it, would never stop going around.
Delicious.
Almost sounds exactly like helium. It's interesting, right? Exactly like the helium-4 superfluidity.
Fluid didn't suddenly become hard. Instead, it's not exactly solid. Think of it like a gel. It's a fluid, but it behaves like a solid.
They've still got a lot to learn about these fluids/solids, but according to their paper, their supersolid, quote, establishes a system with continuous symmetry-breaking properties, associated collective excitations, and superfluid behavior.
Let's break that down.
That's a lot, yeah.
Superfluid behavior you get, we just explained it. Frictionless superconductor.
Collective excitations is a fancy way to say quasi-particles. Quasi-particles are a group of particles that behave as if they're one because their parts are interacting somehow.
And then there's symmetry breaking.
That's also describing particle movement. Normally, in quantum mechanics, symmetry is a big deal. Breaking it, a bigger deal.
At the moment, it continues that old saying, the closer you look, the stranger things get.
But come on, do we really have 6 states of matter now? No, we don't. We have way more. The states of matter, solid, liquid, and gas that you've been living with your whole life were never all there were.
It's kind of like when you're learning math. First, you're taught numbers. Then they tell you there are infinitely many numbers. Then, as if they're just messing with you, they tell you there are infinitely negative numbers too.
And then you find out there are irrational numbers and imaginary numbers.
So it's all really just imaginary if you think about it. Physics in our measurement scale is like basically what we've decided the language to be. We're just creating a language according to what nature kind of is representing, so we can talk to one another about it. That's basically what math is. But let's continue.
And you can do calculations with infinities and embedded equations into each other, and yeah, matters like that.
So yes, solid, liquid, gas, and plasma exist, but it's really about molecular arrangement. Solids are interacting heavily, liquids are more loosey-goosey, and gases are just barely interacting, while plasma is free. It can do anything. But on top of those 4, there are several more states of matter.
Hey Tony, sorry I've been away for a while. Also, what's up Ryan? I did see you there. So I'm just going over like the beginning of this is like my first VCast. I'm gonna start doing, if you have any questions, let me know. I'm gonna start doing this every Sunday and start doing a blog because people keep asking me to do it, and because I got some friends who want to do it with me, and I'll be interviewing people, all that jazz, just to keep you updated on what's going on. I'm still going to be doing my experiments. I'm actually going to be doing more experiments now. I'm super excited about. So there'll be more videos coming soon.
Cold ones like the Bose-Einstein condensate, and supersolid, and hot ones like electron-degenerate matter, free particles found in white dwarf stars, or the theorized stranger matter, possibly found in neutron stars.
Plus, of course, time crystals, which have low energy states and weird effects across time symmetry.
I mean, we should just do a whole video about states of matter, right?
Yeah, we probably should. Bottom line, we have a new state of matter.
So,
Yay, but we don't have 6 or 7. We have.
so this is what goes. Brings me back to the superfluid helium. It's really interesting to think about. All right, Tony. So yeah, this is something to really ponder, like about the idea of supermassive black holes and matter in the universe. Like there's so much going on in the condensed matter physics arena that is, for some reason, doesn't get talked about on the large cosmological scale into the mainstream. Maybe because it's overly confusing for people, but you know, I like to do my best to simplify things to the best of my ability, so more people can understand it. So now we talked about that. Now here's a really crazy thing to wrap your mind around. It's super fluid in. I might not be able to find it on YouTube, but we can try. Superfluid in. Oh, we gotta type it like this. Superfluid in hot water. Let's see, Leidenfrost. If you don't know what Leidenfrost is, it's pretty interesting. Superfluid helium. Yeah, I'm not seeing it. So we'll look into this. It's like basically a structural organization in, I think it's like 40 degrees C. So structured. This is gonna bring up a ton of really out there structured water in 40 C temperature range. Let's see if it brings it up. Physics just discovered a second state of liquid water. Like I found it right there. Nice. So physics has just discovered a second state of liquid water. Okay. It's one of the most fundamental compounds on Earth, and it makes up roughly 60% of the human body, and yet water is turning out to be stranger than we could ever have imagined. Researchers have been investigating the physical properties of water and found that when it's heated to between 40 and 60 degrees Celsius, it hits a crossover temperature and appears to start switching between two different states of liquid. As a chemical compound, water is so vital to life on Earth, we've been underestimating how legitimately weird it is. We have gotten so used to it, it's hard to imagine things getting any more complex than the three basic states: solid, liquid, gas. Under very rare circumstances, a plasma-like state can also form. But in many ways, plain old water is unlike any other substance on the planet. With the exception of mercury, water has the highest surface tension of all liquids, and it's also one of the only known substances whose solid state can float on its liquid state. And unlike almost every other known substance, water expands when it freezes. It also has a bizarre boiling point. So this is where it gets interesting, right? This is kind of what's leading me into what I'm trying to explain and come across, just some things to ponder, right? So while the boiling points of other hydrides, such as hydrogen telluride and hydrogen sulfide, decrease as the molecule size decreases, H2O has a surprisingly large boiling point for such a small molecular weight. No one really understands water Philip ball points out in nature. It's embarrassing to admit it, but that the stuff that covers 2/3 of our planet is still a mystery. See, that's a fantastic scientific approach, in my honest opinion, because that's what science is about, is unlocking the mysteries of nature. Worse, the more we look, the more the problems accumulate. New techniques probing deeper into the molecular architecture of liquid water are throwing up more puzzles. 2 times and 1 time oxygen, maybe the odd electron. Yep. So now physicists have demonstrated that somewhere between the temperatures of 40 and 60 degrees Celsius, or 104 and 140 degrees Fahrenheit, liquid water can switch states, exhibiting a whole new set of properties depending on the state it flips to. So more research needs to be done, but this is directly relating to a lot of the research I've been doing for a while. And one thing in particular is that it creates organization, right? And same principle as the superfluid heliums. You know, it's really interesting to consider that maybe there's something going on there that is creating some of these phenomenons we've seen in the past, a certain temperature range. Let's see if we can kill this ad down here for the viewers. So depending on the state of it flips to. Okay, to figure this out, an international team led by physicist Laura Maestro from the University of Oxford in the UK looked at a number of specific properties of water. They looked at things like thermal conductivity, refracting index, conductivity, surface tension, and dielectric constant. How well an electric field can spread through a substance, and how they respond to fluctuations in temperature between 0 and 100 degrees Celsius. Once the water hit 40 degrees, things started to shift, and properties were changing all the way up to 60 degrees. Each property had a different crossover temperature, somewhere within the threshold, and the researchers suggest that this is because the water had switched into a different phase. The team lists a few of these crossover temperatures, approximately 64 degrees Celsius of thermal conductivity, 50 degrees Celsius for refractive index, about 53 degrees Celsius for conductivity, and 57 degrees Celsius for surface tension. These results confirm that in 0 to 100 degrees Celsius range, liquid water presents a crossover temperature in many of its properties close to 50 degrees Celsius, they conclude. So what's going on here? It's not yet clear, but the fact that water could be switching between two entirely different states of liquid at a certain temperature could be linked to why H2O has such unusual properties in general. Water molecules maintain only very short-lived connections between each other, and these hydrogen bonds are actually far weaker than the bonds that link the individual hydrogen and oxygen atoms inside the molecules. So this is the difference between the Coulomb barrier, right? Molecules bumping against each other and not being able to penetrate each other in views. Luckily, nature has that in place, so everything just isn't on fire with plasma constantly, right? A beautiful balance. This is why we exist, right? So for this reason, hydrogen bonds that link water molecules together are constantly breaking and reforming, and yet within all that chaos, set structures and rules persist. Physicists suspect that this is what gives water its unusual properties, but no one's entirely sure how it works. Everyone is agreed that one aspect of water's molecular structure sets it apart from most other liquids. Fleeting hydrogen bonds, ball rights for nature. Fleeting hydrogen bonds is what they call it. These feeble bonds that link the molecules constantly break and form above water's melting point, yet still impose degree of structure on the molecular jumble. That's where the consensus ends. While Maestro and her team's results will need to be replicated by an independent team before we can start rewriting textbooks to reflect the 4 or 3.5 states of water that could potentially exist, they say their discovery could have big implications for our understanding of both nano and biological systems. For example, the optical properties of metallic gold and silver nanoparticles dispersed in water. So that's interesting that they go back to the nanoparticles of silver and gold, like when we first started this video. So I just lost my spot. The gold and silver nanoparticles. So, for example, the optical properties of metallic gold and silver nanoparticles dispersed in water, used as nanoprobes, and the emission properties of quantum dots used for fluorescein bioimaging and tumor targeting show a singular behavior in the temperature range. They write in the white paper. Oh, they didn't. That's not white paper, but they write in their paper, I should say. It also raises the question of whether temperature-driven structure changes in water after biological macromolecules in aqueous solutions and in particular in proteins, which are the vital functional biological units in living cells. Okay, so let me break that down for you because that's a lot of gibberish. Shouldn't say gibberish, but technobabble. So they use the gold and silver nanoparticles and the fluoresceins to be able to look at the imaging. So they're just looking at the imaging of the structure of the water. That was their purpose, and but it shows a singular behavior in this temperature range, meaning that every time they hit that temperature range, they got the same kind of response and unification, or an organization. There was an organization in the water. There's other papers I've read on this, so that's why I know about it. So, and you can go and look up more research on it. It's really, really interesting. So, and then it also raises the question whether temperature-driven structural changes in water affect biological macromolecules in aqueous solutions. So having a temperature change in a biological structure, like in nature, like if there is a way in your body for the temperature to raise to a certain point, to go past a certain point, maybe there would be some type of different conductive happening, or a trigger or a switch. So like a chemical released in your body that has a reaction, basically, to put it simply, like a chemical in your body has a reaction. Your body gives a signal to have two chemicals interact, and that interaction creates a different hydrogen chain or a different hydrogen molecule to start a new process. So it's like instead of just having a binary code in our bodies, we have another way that we can switch things, which almost like a transistor, if you know much about that, but not quite like it's kind of hard to wrap your mind around. It's like, that's really hard. That'll be another conversation for another time, to go into like a third dimensional computational structures. I won't go into that. But basically, it states that what's happening is when it reaches this temperature range between 40 and 60 degrees Celsius, it's creating a superfluid, and the superfluid has some really interesting properties. So again, it brings into, well, if there's changes in molecular structures in certain temperature ranges, right? What's happening? How can that apply to the macrocosmic world? Like we see it in a laboratory. Well, a good way to do a promising way to do science is, well, if you can see it as a more biblical statement, as above, so below type of thing, right? So, but if you could see it in a macrocosmic scale, hydrogen, right, reaching different temperatures might, perhaps, this is my theory and hypothesis, have harmonic resonance structures, right? Because heat itself is an electrical phenomenon. It's a vibration of matter. Like you've hit a frequency that can move the particles, right? Like the hysteresis of a transformer. An easier way to put it is like a poor performing transformer, where you're actually losing your electrical power, your kVAR, or your optimal performance of your transformer. You're losing that energy in heat and in sound, right? And heat and sound are also very closely related because it's a material vibration, right? Matter vibrates at certain frequencies. So if you can find those harmonic frequencies in which the actual matter vibrates in things like hydrogen and helium, and for example, there's another approach to looking at the universe in regards to condensed matter physics. It's a very, very interesting idea to look over, and hopefully by having this conversation, maybe there's some scientifically minded people that might get a kick out of this and be like, oh, that's really cool, and they have more equipment than I do and can run more experiments. So yeah, that's where I'm gonna wrap up this video, so this podcast, so I don't bombard everybody with just a ridiculous amount of information up front. I hope hopefully this, I like to talk about some deep topics, but this was kind of a more scientifically minded, or technically scientific, kind of like into who I am, basically. This is like what I really care about is understanding the operation of the universe as far as the stars and what we consider black holes and the largest bodies of energy, the life givers of the universe. So, that's if you go back to the beginning of the video or the beginning of the podcast, you can understand more about who I am. For those watching at the end here, I'm going to do these every Sunday to the best of my abilities once again. And I appreciate you guys listening in, those who are listening in, and for watching, those who are watching live. If you want, you can watch live at Conscious Energies on YouTube. Follow me on my social links if you'd like. Instagram, Snapchat, Twitter, it's all Dydenax, my name. You can follow, I'm on pretty much every platform, including TikTok. And so much love to you all, and I can't wait for the next one. It's gonna be fun. I'm gonna probably I'll probably bring on my buddy Ryan on the next one, and he usually spices things up. He's a very opinionated and also pretty funny guy and has a great heart. So he'll be on the next episode. And until next time, guys, appreciate you listening in. Much love to you all, and goodbye.